Welcome to this video. Today I'm going to start with a mesh generation of pipe elbow geometry for next CFD simulation in OpenFOAM and calculation hydraulic losses in pipe. So in previous video tutorial we have created a CFD domain for pipe elbow. You can see this pipe elbow on the screen, and we will be using the exported step file for creation a mesh in Salome today. So today we'll be working with Salome software. I will start with describing where you can download this Salome software. In Google you can just press Salome, and if you will go to salomeplatform.org, here you can find a Salome software. It's also open source, and you can download this software for different operation systems. If you have Windows 10, you can use, for example, portable version or install version. So I use this Windows 10 zip archive. It's a portable version, and you can also download it for Linux, Ubuntu, or another. And let's go to Salome. Here I just extract this zip archive from the site, and here we can to run the Salome. And let's wait some time. And now when Salome is opened, let's go to shaper model. Working like workbenches in FreeCAD. We can choose these different workbenches like in FreeCAD, and the geometry model, it's a shaper, and also Salome have geometry, but it's old model. It doesn't have some parametrical different things. This shaper is something like a CAD designer part workbench in FreeCAD. You can create the different type of geometries here, and also it will be also a parametrical representation. So let's import here from CAD format, and here we have to choose the step format, and let's go to directory where we have our pipe elbow geometry. Here we have to choose our project geom, and here we have the geom point step geometry file. Let's open it, press here OK, and activate the scale to International System of Units. Press OK, and here we have our geometry of a pipe elbow. In part you can see we have one part. This is something like a model, 3D model, which we have here, and some parameters of this 3D model. And here we have our pipe elbow, and the next step will be creation of boundary names for set up boundary conditions for CFD simulation. It will be 3 different boundary names. It will be surface with inlet of a flow, surface with outlet of a flow, and wall of our pipe elbow. So for boundary inlet we will set something like mass flow rate, and on this outlet of the flow we set static pressure. So for wall we will set no slip boundary condition. It means that we will get friction losses of hydraulic losses with interaction between fluid flow and external wall of a pipe. So let's create these boundary names for our geometry. It's similar like in ANSYS design workbench. If you know the software, you will understand easy what happened here. So let's create the groups, and group will be the name of our boundary surface. Let's call it inlet and choose here what we want to choose. It will be a faces. Let's choose this surface, press apply and continue. And how can you see, we have here inlet as boundary name. After that, let's choose here the outlet, called it here outlet, press apply and continue. You will get 2 different boundary names here. And after that, let's choose these 3 different surfaces. You can choose it using shift button and press and choose one by one these surfaces. You can see it here, and also choose for choosing the different geometries. I will delete it, press delete from here, and if I will use a box with left mouse, press and choose all faces, and I can to find inlet and outlet faces here and delete it. Press delete, and for this surface also delete, and we will get only three surfaces here, and these surfaces will be a wall. After that, let's call it wall and press apply. And how can you see here, we have inlet surface and we have the visualization of geometry. Let's hide it, show and hide. You can use it here and choose inlet boundary, outlet boundary and wall. Okay, also you can to see it here, inlet, outlet and wall. Let's check it, the groups, and when we check it, let's go to mesh model. You can choose the mesh here or just choose it in menu here. Let's choose the mesh. We'll close it, and here we have the export of our geometry with boundary names here. Geometry of pipe elbow with inlet, outlet and wall surfaces. So I recommend you to save your project, save document, and let's go to working directory for pipe mesh, and I will save it like a mesh here, save. it will be a file in Salome. If you will get some crashes with software, you can to return your steps if you have some backups of your file project. So let's create a mesh. Here we have to use this icon, create mesh. Let's choose it here, and after that, how can you see, because we choose it in a wall, the last surface, we have here a wall. Let's delete it. Just choose, click here and choose the geometry, and we can see that 3D creation of geometry is available now because we have a solid body of geom here, and we have to activate this create all groups on geometry. It means that mesh automatically will create boundary names for mesh surfaces which can linked with this inlet, outlet and wall groups on geometry. Let's call it in Salome. It's a boundary names of geometry. So let's create NetGAN 3D. It volume parameters of a mesh. Let's click here. Here we have to choose NetGAN 3D parameters, and here we can to set up the values of our mesh. For example, we can set here, we have 0.1 meters the diameter, so it means that if we want to have something like 100 elements per our diameter, it means that we have to use 1 millimeters. And here I want to set something like 50 maybe elements per diameter, and here let's set something like 2 for minimum size, if it will make some smoothness of a mesh with curvature of shape. So let's press OK here. Let's go to 2D and choose here NetGAN 1D 2D. Choose these parameters. Also let's choose here 005, 002. If I remember, yes, we have also these parameters on 2D geometry, and after that press apply and close. Let's create a mesh. Let's try to create a mesh. Click generate and let's wait, and let's look at what's happened with our mesh. But if our elements is small, we will get some very good mesh, and will behave, but it will behave very much number of elements. If you will use this big number of elements, we will get very slow CFD simulation, and you can check what number elements you have. You can go to mesh, press right click mouse and click mesh information here, and how can you see here we have the total number of elements. Something like this value is 500,000. It's not much, but I think for this task we can to decrease the number of elements. For doing it, you can go to mesh and change here the setup of your mesh parameters. Let's increase it to 10 millimeters, and here let's press F5. Let's increase it in 2 times. Let's here 1 and here 5. Let's press OK. apply and close, and you can to recompute your mesh, choose the clear plus compute. And how can you see, the mesh generation is really very fast now, and we have much we reduce the number of elements from 500,000 to 50,000 elements in our geometry. So now we can also to increase accuracy of our simulation for hydraulic losses calculation. We can to create boundary layers on walls, because we have the very big gradient changing of velocity between wall and external flow, and it will called laminar boundary layer. So, and for creation of these boundary layers, we can go to edit mesh, and for 2D geometry we can create a viscous layers here. Okay, let's create a thickness. Let's set a thickness of this will be something like half of our value elements. It will be something like here, this place. We have to set the number of elements. Let's set not much number, and stretch factor, it will be something like changes coefficient of change our layers. Because on wall we have very small thickness for layer, and these layers increase with this coefficient for this number of layers. So let's choose edges which we want to use for generation. Boundary layers. Let's use these layers, and let's press edit here. Let's choose the wall, press add, press OK, apply and close, and let's press click clear and generate and compute. But I think we have some trouble here, because we set viscous layers on this 2D surface. We have to set up these viscous layers for 3D. So let's press none, or just we have to activate it here maybe, but not. I think we have to use this 3D viscous layer setup. Let's go to viscous layer setup for this. Yes, we have the setup, the type of extrusion method here. For pipe elbow we can use any method, it doesn't matter. And let's choose here the setup. I will set 0.05, number of layers will be 7, and stretch factor will be 1.3. And now we have to choose the faces with layers. Yes, and let's choose this wall face. It will choose the faces with layers. It will be 3 faces, how you remember, and press OK. Let's add it here, press apply and close, and let's press clear and compute now. And let's press close, and how can you see? Now we have a correct boundary layers for our mesh, and how can you see? We have the 7 layers here with stretch factor coefficient 1.3. It means that we can see the increase of thickness of these elements to this external flow. So of course you have to set up this thickness boundary layers, depend of type of your flow. It can be turbulent flow with different number of Reynolds. You can to read it in theory in Google it and find the information how to set up this thickness of your boundary layers for getting very accurate simulation. But for engineering applications, very often these parameters not so useful to set up is very accurate, because you will get something like very similar results for your losses. So, and now let's check how many number of elements we have, and we have 100,000 elements here. Let's press OK. It's enough, and it will run on not so the simulation will run not so powerful computer, I think. And now let's check the boundary names for our mesh. How can you see it? Outlet, inlet, and wall mesh. Yes, it looks correctly. These groups of mesh faces. And let's save a project. Press here, and let's export a mesh. This mesh one. Let's choose it, and let's make export. Export we have to make with UNV format of a file, and this UNV format we can to convert to native OpenFOAM polymesh format in the next video tutorial. So let's choose this mesh one, save it, and we will get the UNV file of a mesh here. So it was a finish of video tutorial. Let's close the Salome, and the next video tutorial we set up a case in OpenFOAM and perform a CFD simulation. So thank you for watching, subscribe to the channel, goodbye.